Okay, folks, welcome to the last lecture of the year. I know it is a sad day. It's bittersweet. We're at the end, and we're almost finished your stats class, and I know that's probably heartbreaking. But anyways, let's finish up our hypothesis testing unit here. And today, again, as I mentioned yesterday, or sorry, last class, as I mentioned last class, the class today is basically a little more in depth with hypothesis tests. We're going to go through lots of examples and show you kind of all the different or not every combination possible, but most of the likely examples you're going to see kind of in the near future. Okay, so let's jump in. So first we're going to walk through, and some of this will be review for sure, but the more you're exposed to this, the better, I think. So what we're going to start with is testing a hypothesis about a population mean, where the standard deviation is known and or n is sufficiently large, so n is greater than 201. So remember, that is important. That tells you which test statistic to use, right? So in this case, because we're dealing with a known standard deviation, or we have a value of n that is large enough, then we're using this guy here. We're using the Z distribution versus the T distribution. Okay, and then we'll do an example with the T distribution as well. So first step, as review, we're going to state the null and alternate hypothesis, HO and H1, in terms of the population mean mu, and determine whether it is a one-tail or two-tail test. Then we're going to determine the significance level, which is alpha, to be used to test the claims. And if we're unsure, remember 5% is our default value. We'll compute our test statistic based on the sample mean x bar and the known population standard deviation. So that's our formula here. Number 4, we're going to look up the p-value associated with the computed test statistic and compare the level of significance alpha. So remember, once we have our z value in this example, we have to look it up on the z-score table to determine what our p-value is. And since the test statistic is a z-score, the p-value is equal to the probability corresponding to the negative z-score in the z-score table, regardless of whether the z is negative or positive. So again, that's just something we've already discussed. And finally, at the end, we're going to draw a conclusion about the null and alternate hypothesis and state our conclusion in the context of the specific claim about the population mean that is being tested. All right. So if you haven't memorized those steps yet, don't worry. We'll have lots of practice today to review them. Okay, so first example. We have a drug company that produces over-the-counter pain relief tablets with a mean mass of 600 milligrams and a standard deviation of 3.5 milligrams. Suppose that a company wishes to change the process so that the mean mass will be 625 milligrams instead. A sample of 80 tablets is selected with a sample mean mass of 623.7 milligrams. We can reasonably assume that the standard deviation of the process has remained the same at 3.5 milligrams. So we're going to test the claim that the new mean mass has, in fact, been increased to 625 milligrams at the 5% level of significance. Okay, so what we're going to start with is, of course, our HO and our H1. And remember, we're looking at the claim statement to figure this out, right? So we know for the HO, the mean is going to be equal to something. And then for the H1, it's either going to be less than, greater than, or not equal to. So we're testing the claim that the new mean mass has in fact been increased to 625 milligrams. So the claim is that the weight is 625 milligrams, right? So test the claim that our value is, or our weight is 625 milligrams. So for our HO, we're going to say that the mean is 625 milligrams. Okay. And when we think about our alternate hypothesis, because we're saying that the weight is 625 milligrams, whether it's increased or decreased is actually irrelevant. We just want to test that it is 625. So that means that it could be higher or lower, right? There's nothing here that indicates that it's either just a less than or greater than problem. So we're going to assume that the mean is not equal to 625 milligrams, which is, remember, our two-tail test. Okay, so there's our HO or H1. And our second step, what we're going to do next is identify the significance level. So the significance level So this said we're going to test the claim at the 5% level of significance. So our significance level, that means that alpha is 0.05, right? We're just going to make that into a decimal. So that's our significance level, which will come in handy soon. Our next step is to calculate our test statistic. So again, knowing that we're using a standard deviation that is known in this case, right? So we don't have, so our n size, our sample size is only 80, but we are using the, or in this case, we know the actual standard deviation, which is 3.5 milligrams. So this is one of those rare cases where we actually know what the standard deviation is. I know we talked about how rare that is in the last class, but in this case, we're saying that we know that. So given that we know what the standard deviation is, we're using the Z distribution, okay? So for our Z distribution, we're going to say Z is equal to X bar minus mu divided by our standard deviation divided by the square root of n, okay? So what we're going to do is just plug in our values for that. I should come down here. So our X bar, so what is our sample mass, or sample mean mass? So we're going to look to, we can reasonably assume that the standard deviation has remained at 3.5 milligrams, okay? And then we have a sample of 80 tablets. It has a sample mean mass of 623.7 milligrams. So that is our sample mean. So that's our X bar. So X bar is 623.7. And then we are going to subtract mu. And remember, mu is from the HO and the H1, if you remember that. So that's our 625 milligrams, right? Because that's the claim we're testing. So the whatever we're claiming, that's where that number always comes from for mu. Okay, and then we're going to divide that by the standard deviation. And again, our standard, just to highlight that, our standard deviation was 3.5 milligrams. So 3.5 milligrams. And we're going to divide that by the square root of 80 because we're dealing with 80 tablets. Okay, so let's go ahead and plug that into the calculator, and that'll spit out an answer of minus 3.32. Okay, so that's our test statistic, and then what we'll do from there is to use that to get our p-value. Okay. So let's grab our p-value. Okay, so for our p-value, we're looking at a two-tail test, so that means we're gonna do something a little different with this one. So the p-value, what we're gonna look up is the fact that z is less than, right? So on our z score sheet, we want to look up the fact that z is less than. I'll just plug this in just so we see where that number, just color code the numbers here a bit, minus 3.32. Okay, so we're going to look that up on our z-score table, and on our z-score table, right, we're just going to look down the left side and the top side and figure out what probability is associated with that, and we're going to find that is 0.0005, and I'll just write here from, so we remember z-score table. Again, we've done so much of this, I'm not going to break that out right now, unless you guys do that. So in this case, so there's some rules from the last class where we talked about what happens where the p-value, if it's a left tail, right tail, or two-tail test. So I'm just going to put this here just to remind you that it would be from that section from the last lecture. But the p-value in this case, p-value must be doubled. Okay, and it must be doubled because we have a two-tailed test. So anytime you look up the probability value from the z-score table, the p-value is going to be doubled before we can do any comparisons to the significance level. Okay, so the p-value must be doubled because it is a two-tailed test. Okay, I'm just going to come back here and write some numbers here, so just so we remember the order here. So 1, 2, 3, 4. Okay. So now, yes, the p-value must be doubled because it's a two-tailed test. So now what we're going to say is the p-value is 2 times the 0.0005 that we came up with, which is equal to 0.0010. Okay, so that is our p-value. Okay, so next step, step 5, is going to be to compare the p-value to the significance level. Okay, so we're just going to restate the p-value. So p-value is now 0.0010, and our significance level, we already identified, is 0.0500. Okay, and as a result, just grab a different color here. So as a result, so we'll say therefore, the p-value is less than, because remember we're just comparing these, right? So the p-value is obviously less than the significance level, right? The significance level, 5% is bigger than 0.1% here. So the p-value is less than alpha, which is the significance level. And here I'll just write that. It's going to, rewrite that as significance level alpha, just so we remember what that is. Significance level alpha is 0.0500. And yes, the p-value is less than the significance level. As a result, and this again comes from our notes from last class, we are going to reject the HO as a result. Okay, and remember that with the p-value, when you're comparing it to the significance level, you're just looking at that chart, right? It says if the p-value is less than the significance level, or p-value is greater than or equal to, that little chart, that's where you're going to determine what to do with the HO, to either reject or fail to reject. Okay, so once we compare the two, we've decided to reject based on our chart, and then our last step would just be to summarize, right? So we're going to put a summary statement in here, and we're going to say for part 6, part 6 says there is sufficient evidence. Remember, and we're just restating the claim based on what we decided to do in the previous step. So we're going to say that now that there is sufficient evidence to reject the claim that the mean mass has increased to 625 milligrams, right? So all we're doing is restating, test the claim that the new mean has increased to 625 milligrams. So we're saying because we rejected the HO, right, we rejected the null hypothesis, that there's sufficient evidence to reject that claim, right, to reject the claim that the mass has increased to 625 milligrams, because the HO was in fact that claim. So we're going to add in, it appears, and this isn't necessarily required, but just to bring it all together. So it appears as though the mass is too low. Okay, and how do we know it's too low? We're basing that on the fact that our sample mass was right up here, was 623.7 milligrams. So the likeliness of it actually being 625 milligrams was so low that we rejected that claim that it actually is 625 milligrams. So because what we tested was lower than the original, or lower than the claim amount, we're saying that it appears to be lower. So if that number had been 630 milligrams, and we were testing to see if it was 625 milligrams, we could have had the same result, but we would just say it appears that the mass is too high, right? That's the only difference. So we're saying that it's too low because our sample size, or our sample weight, basically was below what we were testing the claim for. Okay, so that's it. Let's jump into another example. Okay, so number 2. Assume the drug company from the previous question decides to change their process entirely, purchasing brand new equipment to replace their current aging equipment. As such, the population standard deviation is no longer known. A sample of 250 tablets is taken with a sample mean mass of 625.5 milligrams and a sample standard deviation of 5.2 milligrams. Since the equipment is new, the drug company wants to ensure that the equipment is properly calibrated so that the true mean of the tablets will be 625 milligrams, and they want to minimize the probability of allowing under or overweight tablets to be produced. Test the claim that the new mean mass is equal to 625 milligrams at the 10% significance level. Okay. So, first things first. So this is going to be somewhat similar. Some of this process will be the same because we're doing more or less the same question with a few changes. But let me walk you through this just as a review. So for first thing we want to do again is just our HO and our H1. Okay. So we're going to say that the mean is, and again we're testing the claim. So let's go to our claim statement. Claim that the new mean mass is equal to 625 milligrams. So our null hypothesis will reflect that claim, that it is equal to 625 milligrams. And if the claim is that it's equal to 625 milligrams, the opposite, right, the alternate option for that would be that it's not equal to 625 milligrams. So again, we've got our two-tail test here. And again, that makes sense here because the weight of the medication could be too high or too low, which would both have unintended consequences potentially, right? Alrighty. Next thing we'll do is identify our significance level. So in this case, our significance level is, it's alpha, is 10%. So we're going to say it is 0.10, 0.10. That's a little better. Okay. So next, we're going to have to determine which test statistic to use. So, and this is, again, we're going to go back to that chart. All right, let me just put 2 in there. So for 3, this time our standard deviation is unknown, right? So standard deviation is unknown. So that you may be thinking, oh, we have to do the t-distribution, but actually, because n is greater than 201, remember that's our other requirement. It could be one or the other, or both. So in this case, the standard deviation is not known for the population, but n is greater than 201 because we have a sample of 250 tablets. Okay, so in this case, we say that n is sufficiently large so that we can use the normal distribution. We can use the z-score. Okay, so based on that, n is greater than 201. Therefore, use the z-test statistic. Okay, so that tells us which formula to use. So then we'll just plug it in here. So z is equal to x bar minus mu divided by the standard deviation divided by the square root of n. So in this case, remember, even though we don't know the standard deviation, what we end up relying on is the sample standard deviation for this calculation. Okay. So what's our x bar? What was our average? So we had a sample of 250 tablets, and they had a sample mean mass of 625.5 milligrams. Okay, so 625.5 milligrams. And we are going to subtract our mu, which is from our HO and H1 statements, so our 625 from the milligrams from the claim statement. I guess I don't need those milligrams in there, do I? Let's get rid of those. Minus 625. And then on the bottom here, our standard deviation from the sample, we had a sample standard deviation of 5.2 milligrams, so that's what we will rely on for this calculation, right? So now we're going to take 5.2, divide that by the square root of n, and we had 250 tablets. Okay, so we'll plug all that into our calculator, and we will get a z-score of 1.52. Okay. All right, so now let's figure out our p-value. So for number 4, we're going to go to establishing our p-value. So now we're going to look up the probability that that z is less than, right? We're always looking up less than 1.52 for a two-tailed test, because less than or greater than would all be the same. So we're going to always look up less than, and then that is just more direct. It's easier to do. So it's less than 1.52. So from our table, we're going to look up, it is 0.9357. Okay, so that's from our Z table. Okay, so that's below 1.52. Or what we could look up is less than negative 1.52. So in this case, it doesn't really matter which way you go, but remember that the 625.5 is above. It's a positive z-score because it's above the mean, right? 625.5 is above the mean, so of course we're going to get a positive z-score. But what we always want to look up again is the negative z-score, okay? So and that's because we always want the left tail. So for any two-tail test, if I didn't say that right the first time, I apologize, but for any two-tail test in the when we're looking it up on the Z table, we always look for the left tail and then double that, okay? Again, if we looked up the right tail, it would be the same value. It's just, it's easier to look up the left tail because it's direct, right? So in this case, because we have a z-score of positive 1.52, that's actually going to show us if we think back to our z-score, our 1.52 would be here. So that's going to show us this whole value. And remember, we just want the little tail here at the end. So there's two ways to do it. We can just take that value and then say, okay, we'll subtract 1 from it. So we could say 1, from there we would go 1 minus 0.9357, which is 0.0643. And that's probably the more cumbersome way. What I would recommend is just say, if we get a positive z-score, just to make it negative. So this would be my recommendation, is just let's figure out what the probability of z being less than 1.52 is directly, and from the table we're going to get that 0.0643 directly. Okay, so that would be my advice, would be to take it that way, and then it's less, I think it's less confusing anyway. Okay, and of course those rules are all within the p-value section, which we covered yesterday. So if you want to go back and read that, just to reassure yourself why we're taking the left tail, then you feel free, okay? But of course, because it's a two-tail test, we still have to double it. So two-tail test means that we're going to double the p-value. So we're going to take, we can just write that here, p-value is doubled. So we're going to say 2 times 0.0643 is equal to 0.1286. So that is our p-value, and that's what we're going to compare to our significance level. Okay. So remember our significance level was 0.100. So alpha is, I'll just mark this as kind of step 5. So alpha was equal to 0.10, and our p-value is 0.1286. So in this case, we have our p-value is greater than alpha, right? Just larger numbers, so p is greater than alpha. And so as a result, we go to that chart, and the chart says if the p-value is greater than alpha, we claim that there is insufficient evidence to reject the null hypothesis. Okay. And then our last step would just be to rearrange, or to rewrite that claim statement based on our decision here in step 5. Okay. Okay, had to move some things around because it was getting too messy. Okay, so just to sum it up, our final statement would say that in this case, because there's insufficient evidence to reject the null hypothesis, so we can't reject it. What we say instead is, in this case, for this claim, the drug company can reasonably assume the equipment has been properly calibrated. Okay. And again, because the evidence, because we failed to reject, right? We couldn't reject the null hypothesis. So when we can't reject the null hypothesis, and the claim was that it's equal to 25 milligrams, and our evidence said that we can't, our evidence isn't strong enough against it to reject it, then we basically say that it seems to be accurate, right? The drug company can assume the equipment has been properly calibrated because the weight does appear to be 625 milligrams at the 10% significance level. Okay, there you go. Let's jump into the next one. Test for testing a hypothesis about a population mean where the standard deviation is unknown and n value is less than or greater than 201. Okay, so in this case we need both of those to be present, and when those two things are both present, then we're looking at the t-distribution. Okay, so for step 1, it's the same. We're stating the null and alternate hypothesis, HO and H1. Number 2, we're identifying the significance level. We're using 5% as a default value if unstated. Next, computing the test statistic based on the sample mean x bar and the unknown population standard deviation. So now we're using the sample S as the sample standard deviation. So the t-distribution now, right? And again, that's key because you need to know that, be aware of those values or those requirements for actually using the t-distribution versus the z-distribution, right? Because they're both population means. Okay, so calculating p-values for the t-test are done differently than the z-test, so we're going to look at that. And that's really the big difference here when we're using the t-distribution. And of course, it's a different sheet we're using too, right? We're no longer using the z-score table, we're using the t-distribution, so we're going to have a few more rules here. And number 5, same thing. We're going to draw a conclusion about the null and alternate hypothesis. State your conclusion in the context of the specific claim about the population mean that is being tested. Okay, so just going to highlight this. P-values for t-tests are done differently, just so you make note of that. Okay, so now for p-values for t-tests, these are the steps, and we haven't done these yet because we didn't do anything with a t-test hypothesis test involving the t-test yet. Okay, so what we have to do is determine the degrees of freedom. So the degrees of freedom are n-1, which we have done before. We did that in our confidence intervals, and we're going to look up the corresponding row on the t-table. We're going to round down to the nearest degrees of freedom value in the table if it's not found. So that rule is consistent with what we've done before. And you are always going to round down. Okay, so I just put a little note in here. So we don't forget. So always round down. And that's if the number isn't there, right? If the number is there, obviously you take it. But we're always going to round down. And we'll say always round down if value is not listed in table. Okay, and again, that's a specific requirement for this course in this textbook. That can change a little bit. Okay, so number 2, and I'll just highlight that. Just round down. Okay, and then what we're going to do is compare the absolute value. So remember, with the absolute value is just taking the positive, you're ignoring the negatives. Okay, so ignore any negatives. We're always going to look at that as an absolute value. So compare the absolute value of the t-statistic that you calculated to the t-values listed in the corresponding row for the degrees of freedom from the first step. We're going to find the two consecutive values that your t-test statistic falls between in that row, and we're going to call them t lower and t upper, and as they are in the lower and upper bounds for your t-statistic. Third, the boundaries for the critical p-value are the values of alpha for a two-tail test, or alpha split in half, alpha divided by 2, for a one-tail test. In the top row of the t-table corresponding to the t lower and t upper values from the second step. So I know that sounds insane. You're like, oh my God, do I have to do this? The answer is yes, but I'm gonna walk you through. So it won't be so bad once we go through the examples. Okay, and again, I want you guys to have access to this. This isn't anything I need you to memorize. So these steps are going to be available to you kind of from here on out. Okay, so note, if the value of the t-statistic is less than the lowest t-value in the corresponding row, the p-value is greater than alpha equals 0.20 in a two-tail test, or alpha divided by 2 is equal to 0.10 in a one-tail test. Now, if the value of the t-statistic is greater than the highest t-value in the corresponding row, the p-value is less than alpha is equal to 0.01 in a two-tail test, or alpha is divided in half into 0.005 in a one-tail test. Okay, so again, we're going to refer back to this information as we go through. So to practice, for number 3 here, let's determine the range of p-values for the following t-statistics. Okay, and this will just give you some practice to looking those guys up and understanding what we're doing here. So we'll put it into this first step before we jump into the whole hypothesis test. So for number 1, we're going to compute a t-statistic. So let's say we've done the math and we get 2.575, and n is 15, and it's a two-tailed test. Okay, so let's break this one down first. So for number 1, our degrees of freedom is where we start. So degrees of freedom is n minus 1. So in this case, we have 15 as our n value. So 15 minus 1 is 14. So our degrees of freedom we're going to use is 14. Now we're going to have a t lower and a t upper. Okay, so t lower, and we're going to have a t upper. Okay, and our t lower, what we're going to do is look that up on our sheet here, and because our test statistic was 2.575 and our n was 14, we're going to use that information to look up what our upper and lower values would be for that number. Okay, so we switch over here, and we are looking at 2.575 in the body here once we get to a degrees of freedom of 14. So degrees of freedom of 14, let's just draw on here. So we're looking here, degrees of freedom is 14, and remember, we want to figure out where 2.575 lands. So 2.575 would land in between these two, it looks like, right? 2.575, somewhere in there. So that would be our lower and upper values. Okay, so our lower would be 2.145 and our upper would be 2.625. Okay, so that's where it would fall in between. Hopefully that makes sense. So I'm going to go back to our lecture notes here and put those numbers in. So T lower we determined was 2.145, okay, and upper was 2.625. Okay, so what we want to do now is figure out what alpha is, because in this case we have a two-tailed test, so we got to figure what alpha is in each of those values. So alpha, and basically we're just going to go up, right? So we started here, so we can actually see this all the way up here and up here. So alpha is 0.05 for the lower value, and alpha is 0.02 for the upper value. So let's go plug those in as well. So we're going to say alpha is equal to 0.05, and alpha for the upper was equal to 0.02. Okay, and that's how you look those two values up. So what that means is our p-value, so now to put that in as a p-value, our range of values for the p-value would be p is greater than 0.02 but less than 0.05. Okay, so again, our p-value isn't one specific number; it's a range of values that we can compare and compare against the significance level. Okay. All right. So let's see if we can try that again. I know it seems like a lot, but practice it a few times, and again, these steps will be available to you. Okay. So for step 2, now we have a t statistic, which is 3.119, and n is equal to 10, and it's a right-tailed test. So once we have a right or a left-tailed test, a one-tailed test, that means we have to do something a little bit different than the two-tailed test. Okay, so let's start with our degrees of freedom. So degrees of freedom would be n minus 1. In this case, we have n is 10, so 10 take away 1 is equal to 9. So degrees of freedom are 9. And again, we're going to have a t lower, and we're going to have a t upper. Okay. And in this case, we're gonna find those values, but I'm gonna put this in here right now so we remember. We are going to split alpha in half because it's a two-tailed test. So we need to look up what alpha divided by 2 is. Alpha divided by 2 is for this one, and that instead of looking up just alpha, which we did in the first example, right? So now we're looking at alpha divided by 2 because it's a one-tailed test. And again, you'll get used to that as we go through some more examples. So so t lower. So again, or what are we looking for? We're looking for 3.119. So let's go back here and figure out where that's going to clean this off a bit. And we've got degrees of freedom, we said were 9, so that's good, that's easy, that'll be easy to work with here. If degrees of freedom are 9, and we're looking for a t-statistic of 3.119, we can see that 3.250 and 2.821 would encapsulate that value. So we know it's between these two values. Okay, so that's where we're looking at. So that's our lower and upper value. And if we go up, we're going to split alpha in half. So this time our lower value would be, or our higher value, sorry, would be 0.01. And then our lower value would be 0.005. Okay, so those are the numbers we're going to copy back on the class notes here. Okay, so our t lower value was 2.821. And our upper value was 3.250. And when we took the alpha in half, we ended up with 0.01 and 0.005. Okay, so restating that as our p-value, then our p-value would fall between, would be greater than 0.005, but it would be less than 0.01. Okay, so it's not so bad, right? It's starting to get there. Okay, so number 3, we'll do a t-statistic for 1.628, and n is equal to 30. Okay, so degrees of freedom would equal 30 minus 1, which is equal to 29. So our degrees of freedom, we're working with are 29. We'll get our t lower, and we'll get our t upper. Sounds like drugs, our lower and our upper. All right, so let's go over here. Get rid of this stuff. All right, so now degrees of freedom are 29, and we do have that on our sheet here. And this time our test statistic was 1.628. So 1.628, so here's 1.699, 1.311, so there we go. It's going to fall between these two values, and it's a left-tailed test, so it's a one-tail test. So we're going to go all the way up, to both of these columns, and we are going to go all the way to the top, and we're going to get a in half and a in half for each of those lower and upper values. Okay, so again, let's go put that back into our notes. So our lower value we determined was 1.311, and then as a result, alpha split in 2 was equal to 0.10. Okay, and our upper value was 1.699, And if we split alpha in half, we ended up with 0.05. Okay, meaning that our p-value falls between 0.05 and 0.10. Okay, so now you know how to determine p-values for t-statistics. So we're going to do that as part of the the full hypothesis test here as we go through the next example. And I'll refer back to those steps again. Alrighty. So a veterinarian is testing the claim of a pet insurance company which states the average annual veterinarian cost for dog owners is $3,051. The veterinarian believes the cost is lower than this. She pulls bills from the previous year for 20 randomly selected families with dogs that she provides veterinary care for and records the total annual invoice amounts, I should say invoice. She calculates the mean and standard deviation of her sample. Assume the data is normally distributed, and X bar is 2,860, and the standard deviation is $1,112.31. So those were produced for you. You don't have to go through and calculate those from any raw data. Okay, so let's start out as we normally do with our HO and our H1. Okay, so the claim here is that the veterinarian cost is, she said it's $3,051, but her claim is that the cost is actually lower than this. Okay, so if her claim is that it's lower, then that's the claim we're going to test, right? That's it. So, if it hadn't said that part, if it just said the cost was $3,051, then we could test the claim as a two-tailed test and say it could be up or down. But because the veterinarian believes the cost is lower, that's what we want to test. We want to see if it's actually lower than what it has been claimed to be. Okay. So for our HO, we're going to say that our mean is equal to, remember the null hypothesis is always equal to $3,051, but our alternate hypothesis actually reflects the claim, right? Because it's a less than claim. So in this case, we say that the mean is less than $3,051, and because we know that it's a less than claim, we know that that's going to be a left tail test. Okay, so let's go ahead and walk through this one. Okay, so next we're going to look at our significance level. Okay, so in this case, the significance level is not stated. There is no significance level. So remember, the default is alpha is equal to 0.05. Okay, and we say 5% default. I'll just say 5% by default. Okay, so that's our go-to. Okay, so step 3, and now in this case, what are we going to use? We're going to use a t-test this time. So in this case, for step, I shouldn't number those, but 1, 2, 3. So we're using a t-test in this case because standard deviation is unknown. Okay, so, and remember that I know we have a standard deviation there, but the population standard deviation is unknown. We're given just the sample standard deviation. So based on that, we say the standard deviation is unknown, and based on our n value, she's looking at 20 randomly selected families. So we're looking at n being far less than equal to or less than 201. As a result of those two conditions, we have to use a t-test. Okay, so we're going to use a t-test because those two conditions are met. Okay, so that's how you determine that, and of course that's what we're working on, so that makes sense for this example to fall in place. Okay, so for our t-test, we're taking our t is equal to, for the formula, x bar minus the mean divided by the standard deviation divided by the square root of n. Okay, so in this case, x bar would be our sample mean. So if we come back up here, we have a sample mean of 2,806. 60, and we're going to subtract the population mean here, the claim mean, which is 3,051. And we're going to divide by our sample standard deviation, which was 1,112.31, 1,112.31, and we are going to divide that by the square root of n, and we had n as a value of 20. We only had 20 records being tested. Okay, so let's plug that into our calculator, and the calculator is going to spit out negative 0.983. Okay. So remember though, with our t-statistics, we always use the absolute value. So my next step is just going to say, because the t-statistic looks like it's negative, but we're just going to make it positive. So now t is equal to the absolute value of negative 0.983. And if it's positive, of course, you just leave it. So we're going to get a t value of 0.983. Okay? And again, that's because t is always has to be positive. So I'm going to make a note of that and say, let's just move this up a little bit. Because t must be positive. Okay, so we're always going to use the absolute value. So just highlight that and say, okay, there's our t statistic. Okay, so next what we need to do is figure out our p-value. Okay, so let's go back to step 4 now. And now we're dealing with our p-value. Okay. So first thing we have to do, just as we practiced in the previous example, we need our degrees of freedom. So in this case, our degrees of freedom are 20 take away 1. And we've got degrees of freedom of 19. Okay? So what we have to do now is look up this t value of 0.983 and to see where it's going to fall. Okay? So let's go back here. Get rid of all this stuff. All right, so degrees of freedom being 19. So here's 19, and our test statistic, our t value is 0.983. So if we look along here, 0.983 would actually be less than this 1.382. Okay, so when you have a value that's less than, there's a rule to there's kind of a special rule to follow. So let's go back here and I'll write this in. And I want to put this in so we can refer back to it, but you'll have access to this information. So in the t table, put this in brackets, so where t is equal to 0.983, that is less than the lowest critical value, which is t is equal to 1.328. That was the lowest value in degrees of freedom for 19, right? So we're going to put that in. And because of that, we're going to say, therefore, a one-tailed, and this is just from the rules we reviewed previous to the t calculation, so you can go back up and scroll up and read this. So if a one-tailed p-value is greater than alpha and half is equal to 0.10. Okay, so where does that come from? If we go back here and we scroll all the way up, a divided by 2 in a one-tail test is 0.10. So that's where that came from. We're using that value. But we say that because it was less than that value, and we couldn't put it between an upper and a lower value, so we don't have that range. What we say instead is the p-value is greater than 0.10. Okay? And again, just to show you where that came from, scroll up here just for a minute. Determining here, so the little note here, and again, I want you to have access to this, so this is not something you need to memorize. If the t statistic is less than the lowest t value in the corresponding row, the p-value is greater than alpha is 0.20. If it was a two-tailed test, because we had a one-tailed test, we split it in half and made it 0.10. Okay, so that's where that came from. So what we say is that the p-value is greater than that value. So the range is much larger, because it's anything that's higher than that value would we consider the p-value. Okay, so that's where that rule came from, just to remind you. And then what we're going to do is then follow through the normal process here. So at that point, once we figure it, so our p-value is basically anything greater than 0.10, but we still have to compare that with our significance level. So that step hasn't really changed at this point, right? So let's say our step 5 is to compare the two. So if p-value is greater than 0.10 and our alpha is 0.05, that was our significance level, and that was by default, we set it 0.05. When we compare those two, we can see that the p-value must be greater than our alpha, right? So therefore, the p-value is greater than alpha, and anytime the p-value is greater than alpha, we say therefore there is not sufficient, or insufficient, whatever you want to say, not sufficient evidence to reject the hypothesis. Okay, so if we were to wrap that up into a if we were to wrap that up into a nice summarizing statement, we could say that because there wasn't sufficient evidence to reject that hypothesis, right? We can say that there is insufficient. Put this into real words. There is insufficient evidence to refute the claim that the mean annual cost is 3,051. Okay, and I should just, as I write that, I should put up here not sufficient evidence to reject the null hypothesis, because remember, we're always dealing with the null hypothesis, right? So the null hypothesis says that the claim is 3,051, and based on what we found, basically our evidence wasn't strong enough, right? Our sample that we collected, the amount wasn't different enough to refute that claim. So there's insufficient evidence to refute the claim that the mean annual cost is $3,051. So we can't say that that is actually lower. Our sample data wasn't strong enough to refute that. Okay, and that's essentially how we sum that one up. Perfect. Okay, so hopefully you're starting to get the hang of this. that was a little more complex, because again, we got the t statistics in there, which requires a little extra layer of excitement. But again, don't stress out about it, because those rules you're going to have available to you. It's just a matter of going through and determining what the rules say, and then applying it as follows. Okay, so now we're going to jump into some more hypothesis tests, but now we're dealing with a claim about a population proportion. So everything we've done up until now with the hypothesis test has been around means, and now we're going to look at a population proportion. So in order to test a claim about a population proportion P, the following requirements must be met. So we need it to be a binomial experiment. We need n to be greater than or equal to 30, n times p to be greater than 5, n times q to be greater than 5, and p hat, to solve, if we need to make a calculation, p hat would just be n divided by x. Okay. All right, so steps for n over x, that should be x over n. I'll go fix that. Okay, so steps for testing a hypothesis about a population proportion. So You'll notice a lot of these steps are very similar to what we've done. There will be a few differences that I kind of highlight here. So step 1 is still the same, null and alternative hypothesis. We can do that as normal. Significance level alpha, again, 5% being the default if alpha isn't stated explicitly. Next, we're going to compute a test statistic based on a sample proportion p hat, assuming the requirements have been met for using normal distribution. So essentially, we got to make sure that the requirements are met, and then we can go ahead and use the z distribution in using this formula. So again, we're going to use the z-score table for anything with a population proportion. Okay. Step 4 says to look up the p-value associated with the computed test statistic and compare the level of significance alpha. Since the test statistic is a z-score, the p-value is equal to the probability corresponding to the negative z-score. So again, we looked at an example with that previous today, and that rule still follows. So I'm going to highlight that. So the p-value is equal to the probability of the corresponding negative z-score. So remember, if it's an absolute value, we can, or sorry, if it's a positive value, we can just make it a negative value from the z-score table. And that means regardless of whether z is negative or positive, right? So whether you get a positive or negative, we're always going to make it a negative and then look it up. And then lastly, normal rules. Draw a conclusion about the null and alternate hypothesis and state your conclusion in the context of the claim that is being tested. Okay, so that's all similar. Let's jump in and try one out here. Okay, so number 5, and I'm going to tell you with number 5 just to assume that the requirements are met. Okay, so we're just going to go through this and say, yep, requirements are met. Let's go through and solve this using the hypothesis testing procedure. Okay, so we've got a researcher believes that people living in the GTA are at a higher risk of diabetes than the general population in Canada. So a random sample of 400 residents of the GTA is collected, of which 43 have diabetes. Test the researcher's claim at the 10% level of significance if the proportion of all Canadians who have been diagnosed with diabetes is 0.093. Okay, so let's figure out what the claim is. So in this case, somebody believes that everyone in the GTA, or the population of the GTA, is at a higher risk of diabetes. So higher risk of diabetes. So what that means is more people in the GTA get diabetes than the general population of Canada, right? So if we think of that as a claim, he's saying, another way of saying that is that the GTA residents have a greater risk, right? Greater than, so a more than. So this would be, this would be giving you an idea of what we're testing here, right? So we go down to the claim, and it says test the researcher's claim at the 10% level of significance if the proportion of all Canadians who have been diagnosed with diabetes is 0.93. So when we're trying to determine, left tail, right tail, two-tail test, right here it says the claim is that it's 0.093, and remember that anything below that, if 10%, or sorry, if 9%, 9.3% is kind of the cutoff, then anything below 9.3, sorry, anything above 9.3% would be considered greater than risk, right? So when we establish our HO and our H1, our HO is really easy, right? The proportion, now we're using P for proportion. The proportion is equal to 0.093. But what the claim is this guy believes that the GTA people are at a higher risk, so it's a more than claim. So we're actually going to test the claim, right? So the alternative hypothesis reflects the actual claim that the proportion is actually greater than 0.093. Okay, and again, because the null hypothesis could be that it's equal to or less than, right? It could be anything at 9.3% or less, because this guy wants to state that it's greater than for the GTA folks. So that's how we come up with the one tail test, and it's in this case it's a right tail test, a more than claim. Okay. Alrighty. So next we're going to, all right, so that's number 1, as usual, HOH1. Step 2 is our significance level. So in this case, it tells us specifically the claim is at the 10% significance level. So significance level, alpha is equal to 0.10. Okay. So the next thing we're going to do is calculate our test statistic. So again, we assume the requirements are all met, and we're just going to jump into the z-score formula. In this case, z-score is equal to p hat minus p divided by p times q over n, all square rooted. Okay, so let's just make sure we've got all these numbers accurate. So our p hat would be our sample sample proportion. So in this case, if we're looking at this random sample of 400, I'll highlight this, random sample of 400 residents of the GTA is collected, and 43 of them have diabetes. Okay, so 43 out of 400 would be our sample proportion. So I'm going to write that in purple here. So we have 43 out of 400, and we're going to subtract our population proportion, which we're told is 0.093. Right, that's our population proportion. So we're going to plug that in, and that's from our claim statement, 0.093. Okay, and we're going to divide that all by. So then our P and Q here would also come from that 0.93. So I'll keep it with the blue here just so we see that they're all related. So P is 0.093, and that means Q is the complement. So Q would be 1 minus 0.093, which would be 0.907, and we're going to divide all that by 400, which is the sample size. Okay, so put that over 400, and that's all going to be square rooted. So again, make sure you plug this into your calculator properly. You should be able to do it all at once, and if you can't, practice, because it'll save you a lot of writing massive numbers down with decimals, because we don't want to round until the end. So it's going to be approximately 1.00 when all is said and done. Okay, so that's our test statistic is 1. So now, because we're using the z distribution, we're going to pull on our z-score table. So for our next step, we want to figure out what the p-value is, right? So we want to figure out the probability that our z-score is less than negative, and remember I'm making this negative because we always want to look in the left tail end, regardless of whether it's a right tail, left tail, or two tail, right? We're always going to look in the left end, and that is going to be from our table, 0.1587 from said table, just so we remember. Okay, and I know I haven't looked that up in a while in the last few lectures, but we had lots of practice with that. So now I just want to make a written note here that we remember why that's all of a sudden negative. So we're always going to use the negative z value for proportion, say population proportion, which is P, calculations. So that was just one of those rules we just read, right? That's always going to be the case. So whatever you get, positive or negative, we just look up the negative value. Okay. So next, just to follow along with that, now let's compare our p-value to our significance level. So in this case, our p-value is 0.1587. Okay. And our significance level, alpha, was equal to 0.10. Okay. So obviously the p-value is greater than alpha, so p-value is greater than alpha. And then we say, therefore, there is not sufficient evidence to reject the null hypothesis. Okay, so let's put that into some English here. Okay, as a result of that finding, we can say that there's insufficient evidence So again, we can't reject the null hypothesis. And remember, the null hypothesis says that the average, or the diabetes rate for all Canadians is 0.093. So we're finding that there's insufficient evidence to reject that, to overturn that. So to put that into normal terms, there's insufficient evidence to refute the claim that the proportion of GTA residents is the same as the national proportion. Okay, so we can't overturn that claim. So, in other words, the researcher cannot claim that the rate of diabetes is higher in the GTA. Okay, the evidence isn't strong enough. Okay, and that's it for that one. Okay, so number 6. So now we're going to go, just to finish off today's lecture, we're just going to go through 3 more of these hypothesis testing. So at this point, if you wanted to go through and try these on your own and then check with the answers, feel free. If you feel more confident going through with them with me, and then just focus on the homework and the practice questions for your practice, then feel free to do that as well. No worries. Okay, so number 6 says, test the claim that the average dose of a certain liquid cold medication taken at home is equal to the indicated dose of 10 mils. If 219 patients are sampled and asked to pour out 1 dose of medicine, resulting in a sample mean of 10.7 mils with a sample standard deviation of 3.9 mils. And we're going to use a 10% level of significance to test that. Okay, so what is our claim here? So our claim here is that the certain cold medication at home is equal to the indicated dose of 10 mils. So if it's equal to, we'll highlight that. So the claim, we're talking about the average dose is equal to 10 mils, then in this case, we're trying to determine, it could be either higher or lower, right? So based on the results, it looks like people are overpouring for this medication, but that doesn't affect our HO and our H1, because the original claim, the claim we're testing, is that it's equal to. So whenever the claim is equal to, then the alternative hypothesis is that it's not equal to, right? So for our HO, our null hypothesis is that our mean is equal to 10 mils, and our H1 would be that our mean is not equal to 10 mils, again, because it could be higher or lower. And so in this case, we've got a two-tailed test, right? Not equal to. Okay. We were told to use a significance level of 10%, so we'll do that. So significance level alpha is 0.10. And in this at this point, we have to determine which test statistic to use, right? So we're dealing with average. So for a claim of the mean, so we're either going to use a Z or a T statistic. So what we have to look at is the total value of n, right? And whether or not our standard deviation is known. So in this case, we don't see a standard deviation other than the sample standard deviation that is provided. So that's not the population standard deviation. But n is sufficiently high because it's greater than or equal to 201. So because our n is sufficiently high, we can use the normal distribution. Okay, so for our test statistic, just number these again. Got 1, 2, 3. So again, we're going to say because n is greater than or equal to 201, we're going to use the z test, or z distribution, however you want to say it. Okay? So that's how we determine that. That's the formula. So in this case, z is equal to our x bar minus our mean divided by standard deviation divided by the square root of n. And of course, this time we have to use the sample standard deviation. So when we plug that in, our x bar would be our sample mean. In this case, our sample mean is 10.7 mils. So 10.7 minus our claimed mean, which is 10. We're going to divide that by the sample standard deviation, which is 3.9, and divide that by the square root of n, and n this time we had 219 samples. Okay, so let's plug that into our calculator, and we will get an answer of 2.66. So our z value is 2.66 for the mean. Okay. All right, so let's hop up here, and we are going to look at the p-value. So in this case, we're looking at our p-value for z being less than 2.66, which was our test statistic. And from our table, we see that is 0.9961. And because that really doesn't matter, because we actually want the tail, we want above that. I'm just going to put that in. And again, I would probably just skip this step right here. If you did that, great. So 0.061. But we say, therefore, we want the probability that z is less than negative 2.66, which is 0.0039. Again, we could have just taken the complement of that first number, but anyway, that is our value. So what we need to do now is, because it's a two-tailed test, remember the p-value for the mean needs to be doubled. So the p-value is 2 times 0.0039. And I'll just put in here because it's two-tailed. So 2 times 0.0039 would be 0.0078. So there's our p-value for our two-tailed test. Okay, so we'll use that and then compare that to our significance level. So our p-value is 0.0078, and our significance level is 0.010, or we can call that alpha, whatever you want. 0.10 is 10%. And then we have to compare those. So in this case, the p-value is definitely less than our alpha. And whenever that happens, therefore, we're going to reject null hypothesis. Okay, and then let's just put that into a summarizing statements. So therefore, because we rejected the null hypothesis, we can say that there's sufficient evidence to refute the claim that the average dose is 10 mils. Okay, it appears, and we can say that's just based on our sample mean because our sample mean was higher. We can say it appears as though the dose taken at home is greater than 10 mils. So everyone at home cannot measure, they're overpouring their medication, which is not good. But that's essentially our summarizing statement. And again, that's only because the sample mean was higher, right? If that sample mean was lower, we could have had the same results and we could have said it appears that people are underpouring. But our sample says that it's higher than the 10 mils. That was the original claim value. Okay? All right. Well, let's try another one. Number 7. In a poll, 806 adults were asked to identify their favorite seat when they fly, and 492 of them chose a window seat. Use a 0.1 significance level to test the claim that the majority of adults prefer window seats when they fly. Okay. So a couple key things here. We've got a sample of 806 adults, and we're told that 492 of them preferred a window seat. And now we're going to use a 0.1 significance level, which is 1%, right? 1% significance level, to test the claim that the majority, so the claim is that the majority of adults prefer the window seat when they fly. So what do we think the majority means? So we have to know what that means kind of in normal terms. So the majority means greater than 50%, right? So that'll help us determine what our values are here for our HO and our H1. So for our HO, our first step, we're going to say that the mean, right? The mean is, the proportion. We're talking about the proportion because it's the percentage of, right? Over the 50% of adults prefer the window seat. So our proportion would be equal to 50%, okay? And our H1, our alternate hypothesis, would be that the percentage is greater than 50%. So that's our actual claim, right? Our H1 reflects our actual claim because we're testing that it's the majority of adults, so anything greater than 50% would test that claim. Okay? All right, so let's figure out our significance level. Oh, no, of course, it's a right tail test. Right tail test. Okay, so significance level, alpha is equal to 0.01. That's provided there. And then what we want to do is figure out our test statistics. So in this case, because it's a proportion, again, we're gonna assume that all the requirements are met, and we're just gonna go ahead and jump in here, and we're gonna say that the Z is equal to p hat, and remember with proportions we only have the Z as our option, right? So p hat minus p over p times q over n, square root that whole thing, and let's plug in our numbers. So our p hat, our sample proportion, we said that out of the 806, 492 preferred a window seat, so that would be our sample proportion, 492 out of the 806, and we're going to subtract the proportion from our claim, which is 50%. Okay, and then we are going to divide that by, and then our P is still 50%, so that means Q would be 50% as well because they're complements. So we multiply those guys together, divide by N, and in this case the sample size was 806. So divide by 806, we're going to square root that whole bottom, and again we plug that all into our calculator, and we get an answer of 6.27. Okay, so in this case, we're going to go next to our p-value. Okay, so our p-value would be as follows. So what we want to figure out is the probability that Z is less than, and again, I'm going to go directly to this one. We're going to say it's less than 6.27, less than negative, 6.27, because we always want the tail. We don't want anything above that, which we would get with a positive Z score. So we're taking the negative automatically, and that's going to equal 0.0001 or we could call that 0 plus. We know it's really close to 0, but it's not 0, so either one of those would be sufficient answers. And then we're going to compare that to our significance level. So our p-value is p-value is 0 plus, and our significance level alpha is 0.01. So in this case, p is obviously less than that. So we'll say the p-value is less than alpha, and as a result, we reject the null hypothesis, right? So therefore, reject the null hypothesis. Okay, and then we can just summarize that with a final answer. So we can say that there's sufficient evidence to reject. Okay, so sufficient evidence to reject the claim that sufficient evidence to reject the claim that 50%, so the null hypothesis would be that 50% of passengers prefer the window seat. We can say it appears, though, so basically 50% is too low, right? It appears as though the majority of passengers, prefer the window seat. There we go. Alrighty, last question. Last question of the year almost. Here we go. Number 8. Alright, so last hypothesis test. Now we have a nurse is monitoring the bilirubin, whatever the heck that is, levels in an elderly patient who appears to be jaundiced in milligrams per deciliter. So the data appears to be approximately normally distributed. And we have all of these readings. So we can say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So n is equal to 12. We're going to have n 12 samples. So we'll keep that in the back of our minds. And then patients with these levels, these levels above 3 milligrams per deciliter are considered to be jaundiced, which can pose a serious health problem. Test to claim that this patient is jaundiced at the 5% level of significance, and the sample statistics have already been provided for you. X bar is 3.02, and the standard deviation is 0.343. Okay, so let's go ahead and start with our H1. So in this case, our null hypothesis is that the mean is 3 milligrams per deciliter, right? That's what we're looking at, is 3 milligrams per deciliter. That's kind of the cutoff point. But the claim is that this patient is jaundiced. So if we think about what that claim is, so if it's jaundiced, remember the levels have to be above that value, right? So levels above 3 milligrams per deciliter are considered to be jaundiced. Okay, so our alternate hypothesis would actually reflect the true claim, which is, well, not the true claim, but that the claim is greater than 3 milligrams per deciliter. That's what we're trying to figure out, right? So the null hypothesis is that it is 3 milligrams per deciliter. The alternate would be that it's greater than, and that's how we'll determine whether or not this individual appears to be jaundiced. So this is obviously a right tail test, because it's a greater than claim for the alternate hypothesis. Okay, we can easily identify the significance level. We were told it's 5%, so the significance level alpha is equal to 0.05. Okay, as that was already stated, and then we have to go to our tests, or a z-test or a t-test, given that we're dealing with a mean, right? We're testing an average here. So in this case, we have to determine whether we're dealing with a t-test or a z-test. So based on our information here, we know that n is less than or greater than 201, and that we don't know what the standard deviation is for the population, right? We don't have that provided to us. So what we're going to do is then use a t-test, right, as a result. So less than that, unknown standard deviation, so we have to use the t-test. So the t-test is x bar minus our mu divided by our sample standard deviation divided by the square root of n. And in this case, our sample mean was already calculated for us. So we got 3.02. Our claimed mean is 3 milligrams per deciliter. Our standard deviation for the sample was 0.343. And we're going to divide that by the square root of n, and we only had 12 samples here. Okay, so let's plug that into the calculator, and we are going to get 0.20 as our t value. Okay, so now let's go through what do we need to do for our p value based on using the t distribution. So for the p value, okay, we need our degrees of freedom. In this case, degrees of freedom is 12 minus 1 equals 11. So our degrees of freedom will be 11. And then we have to look up where t is equal to 0.20 on our t distribution. So let's see if we can find that. So back here, t distribution, we're looking at degrees of freedom is 11, and we want 0.20. So if we look along the row here, we can see that it's actually lower than the lowest value. So remember, there's a bit of a rationale to solving this. So we'll go back and we can get this from the notes. So because t.20 is lower than the lowest t value, in that case, when we looked it up, that t value was 1.363. It's lower than that value. Therefore, our p value, because it's a one tail, okay, and again, this is straight from the notes, the p value, given that it's a one tail test, is greater than alpha split in half, which is 0.10. So therefore, the p value is greater than any values above 0.10. Okay? And in this case, when we compare the two, so if the p value is anything above 0.10, and our alpha is equal to 0.05, we can see that our p value is going to be greater than, so our p value, oops, grab that pink again. Our p value is greater than our alpha, right? And as a result, we do not reject the null hypothesis. Okay, so the the probability is greater than our significance level. As a result, we will just say, therefore, do not reject null hypothesis. Okay, so what does that mean? So let's put a final statement here. So now that we know we're not going to reject the null hypothesis, so we can't reject the fact that, or we can't reject the claim that it is 3 milligrams per deciliter. So we can't reject that. There's not sufficient evidence. So what we can say is, as a summary statement, there's insufficient evidence to argue against the average level of this word, bilirubin. I have no idea. Can't spell it. Can't say it. Can't spell it. Rough day. Rubin. level of bilirubin being 3 milligrams per deciliter. So there's just insufficient evidence to argue against that claim. So we can say, what does that mean as far as the patient? We can say it appears as though the nurse cannot claim that the patient is in fact jaundiced. Right? The evidence just isn't strong enough to indicate that definitively this patient is jaundiced. Okay, so there you go. I want to wish you luck with the homework and all the practice up until your final exam and your assignments and everything from here on out. You now have all the tools to solve the problems that are coming your way. And of course, I'll be available to give you a hand if necessary. All right, so we will see you soon.